I'm going to share my screen. Guys. Okay, so I hope you guys can see that. I'm going to click play, I think. I don't know. For virtual, I don't really know which one to pick. Teach? I don't know. And classic. Okay, I think that worked. Oh, no worries. All right, so just join this Kahoot thing if you guys get a chance. And we're gonna talk, I'm gonna talk you guys through all of these, okay? So we have 16, I think actually 14 people in here, so 14 players. Okay, I just need a few more minutes to get in there. Seconds. I'm looking for one more person. Oh no, 13 is the exact number. Okay, I think we're good because my phone counts as one. All right, so that's it. So we're gonna get started. I can figure out how to click play. All right, here you guys go. We'll talk it through. So Sn1 or Sn2 is the question. Ignore E1, E2 for now. What do you guys think? All right, awesome. So let me just explain that one more time real quick. So you guys recognize that the first thing you want to do is classify this starting material. So I see a primary. Don't even think any further. Primary means Sn2 every time because it is sterically unhindered, okay? So that's a big hint that it is going to be an Sn2 pathway. Also, if you were to separate those two ions, sodium and the sulfhydryl group, sulfhydryl has a complete negative charge. We said negative charge things are good nucleophiles, so that is good for Sn2 conditions. And also, DMSO is a polar aprotic solvent. So again, more for Sn2. Good job. Awesome. All right, try this one. Waiting on one more person. Awesome. I don't even have to explain this to you guys. But again, tertiary. Okay, so tertiary means Sn1. We're not even there yet. And also we see that this is both our, nucleophile and our solvent. And it's both weak because I don't see a full negative charge. And it's also a polar protic solvent because of the protons of water. Again, all Sn1 conditions. Great job. So we would also expect with that one an E1 product as well. Okay, so Sn1 comes with E1. All right, good job, guys. All right, let's keep going. Okay, so a little bit trickier now. First thing you do, classify that starting material, classify that nucleophile as strong or weak, and then think about that, what that solvent means for our nucleophile. So we're a little mixed here, but overall, good job. So let's explain this. So this was secondary. So this was my gray area. I didn't really know, okay? So it could be either or. But when you take that sodium away from this ester or this carboxylate, anion, it's a complete negative charge, okay? So that means it's a better, nucleophile, than the weaker ones. And acetonitrile says that it's weak. A polar aprotic solvent. So polar aprotic solvents enhance the nucleophilicity of that nucleophile so that it can do a backside attack in an Sn2 fashion. Hopefully that makes more sense. We'll see more of that, but good job. All right. So so let's talk about this one. So tertiary, no thinking. So I see tertiary group. I know this isn't a chiral center. I don't know why we have wedge dash here, but it's a tertiary center, okay, which means it's Sn1 conditions. It's sterically hindered, so we're not going to be able to directly backside attack like that. We have a weak nucleophile, and we have also a polar protic solvent, so Sn1 conditions. First thing you always do, remember, classify that starting material, okay? And what is that nucleophile doing? Let's try and get some better at, let's get a little bit better at this. So, okay, tertiary, okay? So that means that what's gonna happen here is an Sn1 pathway. This center is too crowded for any nucleophile to approach it. So the only option for it to happen is for this bond to break on its own and carbon dioxide leaves. Okay, so CO2 just goes away. Then you're left with a carbocation at that position. And now, since that group left, we are able to have nucleophilic attack at that center. And then we get this ether product. So it's Sn1, okay? Sn1. Anytime you see like crowded things, it's Sn1. If you don't see crowded things, it's Sn2. Okay. Good job, everybody. Sam, you're on fire. Classify that starting material, classify that nucleophile strong or weak, and then classify what that solvent's gonna do. Awesome, you guys are getting it. So again, real quick, secondary, that's in my gray area. Azide, which is N3 minus, is a very strong nucleophile, DMF polar A protein. Good job. All right, we have a few more. The goal is to get 100, accuracy at some point. Users are getting faster to respond too, so I can tell. Awesome. Okay, again, tertiary, weak nucleophile, polar protic solvent. Okay, a couple more. Okay, so be careful here. I knew this was going to throw some people off. So let me explain this. This is a very common trap. So I'm happy this happened. Okay, first of all, this is a secondary. Okay, so it's my gray area. I don't really know what's due. But I see over here I have my O minus, which means it's strong nucleophile. But why do I have a polar protic solvent with a strong nucleophile? Isn't that kind of, isn't that kind of the opposite of what I want? Okay, well, the thing is that this, every time we have something called an alkoxide anion, so that's what this kind of ethyl O minus is. It's just alkoxide, ALKOXIDE, just basically is the anion or the deprotonated version of an alcohol. Okay, so you can look at ethanol, ETOH is ethanol. So it's 2 carbons and OH. Anytime we have these alkoxide nucleophiles, they're typically dissolved in their protonated solvent. Okay, so there would be more of this obviously in solution than there would be of ETOH. But what we're saying is this is the only example where we'll see a very, very strong nucleophile with a polar protic solvent, these alkoxide O minus anions. Okay, does that kind of make some sense? It's just the protonated solvent is kind of what it's dissolved. And yes, you can argue that it decreases the rate of an Sn2 reaction, but this is definitely not going to be Sn1. Definitely not going to be Sn1. Okay? Does that make sense? Okay. Awesome. Okay, a couple more. I'm going to go over it. You guys got it. I'm going to keep going through this. You guys are clearly getting the trend now. You guys are seeing like, wow, Eileen, awesome. Let's talk about this. Okay, so secondary, my gray area. Strong nucleophile with this negative charge, polar aprotic solvent won't solvate this at all. It makes it this really strong. It can do backside attack, Sn2. This one. So we just talked about this. One more person. Let's talk about this. So again, I guess if you're getting a little bit confused with that solvent, okay, the most important thing is the substitution of that reagent, that starting material. If that substitution is a primary or a methyl, it's going to be Sn2, don't even think. If it's going to be a tertiary, it's going to be an Sn1, don't even think. If it's secondary, you have to think, okay? So then if you're looking here, you see this O minus, that's a strong nucleophile, can directly backside attack and kick that off. It's dissolved in this polar protic solvent. This is the only example that we're going to see because it's typical for alkoxide anions to be dissolved in their fully protonated alcohols. Okay, good job. Awesome, Hannah. Farah, you're still up top. That's awesome. All right. You got 2 more or 3 more? Okay, so this could be tricky. You know, first identify what your leaving group is. Yeah, see, it's a couple different things. So my leaving group is that carboxylate group. Oh, say it. You guys got it. Oh, I think there's stuff going on in the chat. Oh, I'm sorry. I just saw this. Could we also use E2 for that, Kate? I'm sorry. I missed that one. Do you remember which one it was?
Yeah, it was for question 8, and it was the one where it had the polar protic solvent with it. And I think it was a secondary carbon. So
okay.
I was wondering.
You remember it was number 8?
Yeah.
Okay, I can pull it up after we go through all these questions and go back to it.
Okay,
for sure.
thank you.
Mm-hmm. Okay, I got 2 more. Okay, so remember, pH versus Cl, which one's my leaving group? pH just stands for phenol, P-H-E-N-Y-L, the benzene ring. So secondary, okay, my chloride is going to be my leaving group, not my phenyl group, which is a benzene ring. It doesn't make sense for benzene to just leave. But we see once that sodium spectator ion dissociates from that alkoxide anion, we have a full negative charge, which means it's a strong nucleophile. And yes, ethanol is a polar protic solvent, but here's another one of those examples where, you know, this is the situation. It's Sn2. All right, awesome. Last one. Okay, this is a terrible question. I see so many issues with this. I'll talk about it when I finish this. I'm sorry. So this is actually the elimination product. This is E2. Okay, so this is exclusively E2. This is a bulky base. I don't know why this is in here. I think I just wasn't paying attention. So this is a bulky base, which means that it can only deprotonate, you know, a proton from the adjacent position, donate that electron density in, and facilitate the removal of that leaving group. Now, if you guys were remembering from last class or whatever, what is our rule, Hoffman or Zaitsev, for this specific example that we're going to follow? Somebody wants to put it in the chat. Hoffman, yes. Okay, awesome. So we normally think to do Zaitsev because that would be like the more substitute position, but one constraint of elimination 2 is that we're using these bulky bases, which kind of restricts where we're able to deprotonate, okay? So we have to hit the less sterically hindered side, you know, get rid of that proton and then facilitate the removal of the leaving group. Awesome. But overall, great job. Who won? Let's see. Exciting. Awesome. You got all, oh, you guys get them all right? Wow. Hannah, that's awesome. And Sarah, you guys got all them right. You guys rock. All right, runners up. Congrats to congrats everybody for doing this. All right, so let's go back to the workbook and we're going to do a whole bunch of problems now. Okay, so I'm going to switch over. Actually, I'm actually going to show you something else I want you to take screenshots of. Stop sharing. 1 second, guys. And I wanted to show you. 1 second, guys. We wanted to go back to that number 8 example, correct? I think. Let's go back there. Okay, so on number 8, we had, and I'll share this again with you guys. Number 8. So where'd Zoom go? Share with you. Okay, so you see this. So we were on 8, I believe, and this was so we were asking if this was a potential E2 product. Okay, this wouldn't be. I like Sn2 for this one because it's not one of those bulky bases. You guys are only, when you're doing E2, it's going to be tert-butoxide, like that, TBUO, or it's going to be LDA. Okay, so this probably wouldn't do the E2. I'd be more inclined to say Sn2 for this one. Okay. Does that kind of make sense, Kate? I think that was your question, Kate. I'm not really sure.
Yeah, I guess though, because like in our notes and stuff, we have E2 reactions with like NaOH and like I guess smaller strong bases like that, and it's like a strong base with its conjugate acid as the solvent. And so like at first glance looking at that, I would also think like E2.
Okay, so you would have thought E2 originally as well for both those examples. I guess the best thing I could tell you is that you're only really going to deal with E2 if it's really, really branched. Like there's that example in the workbook, and we'll see it again today, where I did like 4 carbons. Like this is 2 carbons ethyl. Like it's not that heavy. You know what I mean? If you had 4 carbons, like which is the example in the book, or something that's really bulky, it's not going to be nucleophilic enough. But this is definitely nucleophilic enough to do Sn2.
Okay.
We'll see more examples. Hopefully I'll clear it up. Okay. And I want to show you guys that thing to screenshot. This is going to just some extra tips for you guys. Okay, so I made this way back when I was like a baby TA. So hold on, show this. Okay, so you guys see all that? So I can scroll down. So this is kind of, some just words to put to all of this. And this like 2-page document, like literally saved so many people. Like when I first started doing, started teaching Orgo 1 and 2, like it really kind of puts it all together. I know it's abstract. It's definitely an abstract topic, but this kind of explains the logic behind it. So take a screenshot from there, question 1. Okay, and I'll move on. Okay, so question 2. So this is just talking about the difference between the definitions, the kinetics, things like that. Okay, so everyone gets that for a second. All right, and then we have more of that, so stereochemistry and other considerations that we want to talk about. And that same graphic that I drew for you guys earlier is provided below. And maybe this kind of, and this is now here, it's called the pink area. I don't know. Gray area, blue area, pink area, whatever. Okay. Okay, so again, I would really, look at this last kind of bubble. This is the most important thing to take away. If we have a molecule that resembles this pink region, so something that's secondary, we could potentially have either Sn1 or Sn2 conditions. What else do we need to consider? Well, first consider that nucleophile. Is it strong? Is it weak? Remember, strong would be Sn2, weak would be Sn1. And after that, if you still want some more clarification as to what it is, you could just look at the solvent. If it's a polar protic solvent, typically it's Sn1. Notice how I said typically. If it's a polar aprotic solvent, it's typically Sn2. Remember that one specific example where we see protic solvents with a very, very strong nucleophile, and that's only with the alkoxide. Okay, Sn1, Sn2. I hope we're all good on that. Right, and that's all I have for you. And I think there's some questions in here. Can you please show question 1? Yes, question 1. This is better for you guys. Okay, you guys, everyone has it, I hope. Awesome. Any questions up until this point? Awesome. All right, I'm gonna switch to my phone now and we're gonna do some questions in the workbook. Yes, I could redefine alkoxide. So what I mean by alkoxide is it's essentially this. I know this is a chapter 10 word, but I know you guys encounter them now. So this is an alcohol. This is the alkoxide anion, okay? Just like you call this water and you call that hydroxide, it's just this is alcohol and this is alkoxide, like al for alcohol, and then oxide, you know, meaning like anion. So that's literally all it is. Does the length of the chain matter? Yes, it does. So we said that the more branched or the heavier that it is, so something maybe like, let's say methyl, so let's do this, H3CO versus, and we'll do this when we get to these questions, versus maybe, I don't know, something like that. So look how extensively, you know, bulky or look at this extensive carbon branching that we have over here versus just one simple methyl group. There's 1, 2, 3, and then this rest of the carbon chain. This would be a very weak nucleophile in terms of, you know, nucleophilic properties. This would be a very strong nucleophile, okay? So the chain length definitely matters, okay? Are you guys good on what alkoxide means? Now, I hope. All right, so let's move on to these questions here. So the first thing is rank the following leaving groups on their ability to participate in nucleophilic substitution reaction. Okay, so something, I'm just gonna give you guys a little bit of a preview. Look at page, if you guys have this, page 127. This is so common, I can't even tell you. I can almost guarantee you're gonna have this on your exam, okay? So like, know how to do this. So what are the effects of changing a leaving group? What are the effects of changing this solvent? What are the effects of changing this nucleophile on this overall reaction? Is it gonna go faster, slower, no change? So we're gonna talk about all of these things in isolation today, and we'll piece this all together next week, hopefully. So just, that's an idea of where we are. Anyway, so which ones are the better leaving groups? And that's gonna help you later on, clearly. So the better leaving groups are the leaving groups that are the most stable. So I'm gonna write up here, most stable. That makes sense. Something will leave a molecule if it's stable on its own and it's stable enough to exist on its own, okay? So let's think about the stability of a bromide anion, a fluoride anion, and a chloride anion. So going down the periodic table, clearly, these are the halogens: fluorine, chlorine, then bromine. Okay, so fluorine's at the top, then chlorine, then bromine. So what's happening as I go down my rows in the periodic table, I'm increasing principal quantum number, or I'm basically increasing the number of shells or the size of that anion. We said the larger that size, the more space to accommodate that negative charge because there are more protons there, all of these things. So the larger that anion is, the more stable it is. So since bromine is the biggest, it's going to be 3. Since chlorine's the next biggest, it's 2. And then fluorine is 1. Okay. So that was just this so far. Let's look at the next. One is like the most stable on its own. Well, the one that's most stable is the one that definitely doesn't have a charge. Okay, that's easy. That's stable. We know water exists on its own. But between hydroxide and carboxylate, which one is more stable? Well, there's one feature, and put it in the chat box. We've said this all semester long now. One feature that makes one more stable than the other. Resonance. Perfect. You got it. Resonance. You guys rock. You guys are like my all-star, like 14 students. I love it. Okay, so because we have resonance here, this can definitely, you know, be stabilized. That negative charge can be delocalized over the ring. So that makes it the next best. And then, you know, hydroxide is still decent, you know, in terms of, I mean, hydroxide is a bad leaving group, but hydroxide is like a good nucleophile. You know, okay, so anybody have questions on A and B? Okay, so again, kind of same situation here. We have 2 negative things and then 1 neutral thing. So clearly the neutral thing, I'm not even gonna think. The neutral thing is obviously more stable. Okay, negative charge things are not stable. Okay, again, the resonance thing. Can I resonate with this amide? Yes, I can. Here you can't. So 2, 1. Super easy, okay? Let's move on to 2, if you guys have questions. So that was, you know, leaving group stability. So actually, let me just talk about this one more time. So the more stable that leaving group, the faster the rate, okay, the faster. So, you know, if I had some sort of reagent with a bromide and a bromide, you know, substituent versus the fluoride substituent, the Sn2 maybe reaction or the Sn1 reaction is going to go a lot faster for these, you know, better leaving groups than the weaker leaving groups, okay? Rank the following nucleophiles in order of increasing strength. Okay, so we're going to omit this one. Okay, Dr. Peterson wants us to omit that because, you know, it has similar stability to one of them. Okay, and what we want to do is we're considering the acetone as the solvent. Okay, so what does acetone look like? Okay, acetone is that solvent. Okay, and if acetone is the solvent,
it's protic, okay? So we have all these protons, okay? And these are actually acidic. This isn't one of those examples. It's not DMF, it's not dimethyl sulfoxide, which is DMSO, it's not acetonitrile, you know, it's acetone, okay? So what happens is we need to think about the identity of that anion, of the atom that bears that negative charge, and the carbon branching that's going on. So first, if I were to dissociate those spectator ions, I get a negative charge on all of these. And remember, we're thinking Sn2, so that is a big key. So when you look at these questions, look what the solvent is. The solvent's acetone. So I'm thinking Sn2. Which one's the best one for an Sn2 conditions? Well, we know Sn2, the stronger your nucleophile is, the faster that rate is going to be. I think I have a question in here. Since it, Farah, is that a question? Oh, you're good. Don't worry about it. Okay, so negative charged on a sulfur versus a negative charged on an oxygen. Okay, so a negative charge, I think I have a whole bunch of messages in here. What's this? Okay. So the negative charge on the sulfur versus a negative, so oxygen is above sulfur, so sulfur is a little bit larger, okay? So we have 4 for this one, so Sn2, with the HB aprotic. Yeah, and that's why you can tell I'm like having a little bit of an issue with this for a second. Is acetone one of those salts? Give me 1 sec. I'm gonna look this up real quick. See if acetone is acetone aprotic or protic. Okay, acetone is polar aprotic. Okay, with the HB aprotic. Yes, fair. That is correct. Okay, so acetone is aprotic. So that means that since sulfur is a larger atom, I'm looking at this back. Since sulfur is a larger atom than oxygen, I don't know why she ranked these this way. I got it. Okay, so this is the rationale that you guys want. Sorry that it took me so long to get there. So essentially, what it is, you know, sulfur is larger. Sulfur is a bigger atom than the oxygen atoms would be, but it's the best one because if you think about it, as you increase, you know, principal quantum number, or as you go down, you know, the periodic table, you're decreasing electronegativity. Okay, so if I'm decreasing electronegativity, I'm more capable of donating these electrons to, you know, do nucleophilic substitution. Oxygen is more electronegative, so it's more likely to hold onto those electrons. And, you know, when deciding between these two, the bigger one is slower, so that gives me 3 and 2. Okay, just kind of follow that so far, and 1 would have been that one or something, but okay. I'm sorry that took me so long. This was aprotic, okay? And then also because this is larger, it's less electronegative, meaning it's more capable of, you know, donating to something. Okay, so let's keep moving. So for this guy, same thing. So they're all oxygen, so we have to think about that. And then clearly all we have to consider is sterics. So this one is, you know, the smallest, then this one, then this one, then that one. That was that easy. Okay, so for C, we have a whole bunch of different things. Okay, first of all, what does this positive charge mean? Somebody says this in the text box. I'll be really impressed. Why is that positive charge a big hint for you on this question, or a big hint to tell you where to start? No, it has no, boom, no electrons to give. Perfect, electron, yeah, perfect. All these things are great. So no electrons, there's no lone pair. So it's not even a nucleophile. It literally is not a nucleophile, 1, that's it. So that gives you a good starting point, okay? So that's kind of a trick question, I guess, right there. There are no lone pairs, so it's not even a nucleophile. Okay, so out of these all have lone pairs. So remember, the more electronegative something is, the less likely it wants to be a nucleophile. Okay, that makes sense. The more electronegative it is, the more likely it wants to hold on to it. Okay, so, you know, sulfur is the least electronegative out of all of them. Then I think, nitrogen is, and then oxygen, 2. Okay, yeah, so if you look at the periodic table, sulfur is below oxygen, and nitrogen is to the left of oxygen. So 4, 3, 2, 1. Any questions there? Awesome. Okay, keep going. So these 3 are going to be Sn1 conditions. Let me just. Okay, so we're assuming water as the solvent. So water is protic in this situation. So remember, consider all of these starting materials. So before we were ranking nucleophiles, okay? Now we're ranking starting materials. So we know for an Sn1 condition, an Sn1 reaction to happen, what intermediate are we going through? Carbocation. Okay, so the more stable the carbocation is, which we've seen this question like done in multiple different ways at this point, the more stable that carbocation, the faster that reaction rate's going to go. Okay, so clearly, if I were to remove this bromide and form a positive carbocation there, it's tertiary benzylic, clearly the fastest. Here, secondary benzylic, next one. Then this one would just be a plain secondary, and this one would be a plain primary. Okay, and that's how I would rank these. Questions on that one? Just carbocation stability. That's all we're doing here. Okay, so this one would be a tertiary. We're going to assume, remember, we always assume that the secondary allylic is better than tertiary. So this is a secondary allylic once that bromide leaves. This is a tertiary. This would be a secondary, and that would be a primary. Okay, so far. And again, Dr. Peterson wants us to omit this one, okay, because it has similar reactivity. So just focus on these three. Okay, so then when that chloride leaves, we see that we're going to be, a positive carbocation there, but it's also destabilized via induction. So it makes it, the weakest. I would have called it 1, if I was doing 1, 2, and 3, but we're starting with 2. Here we have a plain secondary. Don't be fooled, that pi bond doesn't do anything. It's too far away. But here we have a tertiary. So 4, 3, 4, 3. Okay. Tertiary, secondary destabilized. Okay, I hope that all makes sense so far. Okay, now we're going to rank more reagents, Sn2 in an Sn2 fashion, and assume DMSO as the solvent. Okay, so now we basically have to think about first the leaving group. Okay, so this is not carbocation stability. This is sterics A. We're thinking sterically, and we're also thinking about the identity of that leaving group. So is iodine or chlorine a better leaving group? Well, iodine is bigger. I think it's below. So it's more stable as its own leaving group. So this is definitely the best one. Okay. And then now everything else is just sterics because remember it's Sn2. So the worst one, the next worst one, and then the best one, the better one. Okay. Any questions there? Awesome. Okay, and then same thing here. So now we're going to rationalize these leaving groups. So clearly the halogens are going to be the better leaving groups than these hydroxides or sulfhydryl groups because these halogens are just single atoms, and when they leave, they have their full valence octet configuration. So yeah, that is so stable. It has all 8 electrons. It's basically that noble gas configuration now. So chloride, reagents and iodine reagents are definitely going to be the top 2 that we see. So out of iodine and chlorine, which one is better? Well, iodine is bigger, like we said, than chloride. And then between hydroxide and sulfhydryl, remember which one's bigger? Sulfhydryl is bigger. So it's more capable of accommodating, that space of that negative charge. And that's where we are. Okay, remember we're still on Sn2 conditions, so for C we're just thinking sterically. So we have primary, best one, not even thinking there. Then I see secondary, okay, next best one. Then I see tertiary and tertiary, but that's a crazy tertiary with terbutyl, so 2 sterically hindered. Okay, I think that's pretty easy now that you guys know what to look for. So Sn1, look for carbocations, Sn2, look for sterics. Okay, so now talking about nucleophile strength. Okay, so for the following pairs of nucleophiles labeled A through E, we're going to decide which nucleophile is best for the Sn2 reaction. We're assuming acetone is a solvent, okay, so that enhances the nucleophilicity. Okay, so we said that the time when we have a complete negative charge on something versus not having a negative charge on something, it makes it a very good nucleophile. So no thinking, that one. Okay, fluoride and bromide. So remember, fluoride is really, really tiny, okay, really, really electronegative, and doesn't want to give off its electrons. It's very high up in the periodic table. Bromide is a little bit further down, less electronegative, more capable of donating those electrons, okay? Here we have tert butoxide, bulky base. Here we have ethoxide, okay, the alkoxide anion of ethanol. when we're determining between these two with different branching patterns, the less branched nucleophile is the better nucleophile, because we use that, track analogy. Remember, if you're running and you're doing this strength training and you have these parachutes weighing you back, you're not going to be able to do nucleophilic attack as good as the guy that doesn't have the parachute on. Okay, so then if you have the same substitution, then we just have to think about, the identity of that atom, and it deals with electronegativity. So since nitrogen is less electronegative, it's more likely to donate electrons and be a nucleophile. Okay, and we're going to rule out E because E has similar, nucleophilic properties in real time. Okay, in terms of like actual quantifiable data. All right, so now we're going to do some predicted products for Sn1, Sn2. So just a word of caution here. I wrote in these directions, ignore potential elimination products for now, because typically in a given semester, like people do this as they go. Like, so you learn Sn1, Sn2 first, and then you deal with the elimination stuff. So right now, we're just going to talk about Sn1 and Sn2, and we'll ignore any elimination stuff for now. And we're going to, on an actual exam though, you'd be expected to provide both. Okay? So first things first, secondary. Okay? What is this nucleophile? Strong. Aprotic. Okay? Those are the three things I would write down. Sn2. Okay? We know Sn2 is going to be a concerted mechanism where the sulfhydryl group attacks that carbon and that chloride leaves. Okay, but remember, it was sterically hindered on the dash orientation, so we could have only came from the wedged orientation, so we exclusively get one product. Okay, and that is my Sn2 product. Okay. B. Okay, B. Tertiary. Weak. Protic. Three things. Sn1. Okay, we know Sn1, the rate determining step is dependent on, this intermediate forming. Okay, and then you can imagine the lone pairs of this coming and attacking. Okay, and if you want the full mechanism, you can always assume excess reagent. That excess reagent gets rid of that and makes that ether. Remember, this is not a chiral center, so we would just expect, that product. Sn1. Okay, for C, we see primary, we see strong, we see aprotic, so we think Sn2. Okay, there's no stereochemistry to consider here. You're done. Okay, let's keep going. For D, okay, we see that phenyl is not my, leaving group, but my carboxylate anion is. So that's secondary. This is sodium azide. So N3 minus means it's strong, and acetone means aprotic. Okay, that all tells me Sn2. Remember, the mechanistic step is backside attack. So we would get azide. So a word, I guess a little word about azide, N3. N3 is a really, really good nucleophile, azides. Azides really are like, I forget the exact Lewis structure, but I think it's like something like that, and I don't really know. But it's these N3, and essentially it literally is shaped like a bullet, like in terms of its electron geometry. So like you can understand why azide is so good at nucleophilic attack, especially N3, because it's this bullet, tiny, compact, relatively low in electronegativity compared to like all these other nucleophiles. So just something to know. Okay, so then here we see secondary. We see, this is probably strong-ish. Okay, and acetonitrile is aprotic. Okay, all these things tell me Sn2. Remember, this is not an exact science. We're just kind of like using what we know to like predict if it's Sn1, Sn2. Okay, so you should expect. Okay, so then here we have tertiary, weak, protic, Sn1. Okay, that rate determining step is that chloride leaving, and then that propoxide group is going to come in. 1, 2, 3. And remember, it's achiral because it's not a chiral center. Okay, so we're going to move up. So G, so we see tertiary, weak protic. Okay, so a consequence is you lose the stereochemistry that you had in your starting material. Okay, so why is that in this situation? So look, when that bromide leaves, you get now this carbocation at that tertiary position. That carbocation, remember, is planar, sp2 hybridized, 120 degrees with an unhybridized p orbital. So now water could have attacked at the top face of that p orbital or the back face. So we get a mixture of these diastereomers. And it's called like racemization, okay, racemization. And it basically means that you get a racemic mixture with respect to that carbon. I hate saying that word because these are diastereomers specifically, but it's called racemization because it's the racemic, like, I guess, fact that that original reactive center is now, you know, these two RNS configurations. Okay, so racemization, maybe I'll write that out, racemization. Okay, so again, azide, we talked about that. Strong, aprotic, secondary. Azide on the back, easy. Here, okay, we have primary, strong. Relatively, this branching is getting a little too much for me, okay? We don't have cutoffs. I wish I could give you a cutoff and tell you like what exactly is strong and what exactly is weak, but I know for a fact 4 is too big. And I know 3 sometimes works, okay? And complexed with this primary, you know, reagent, you know, I would definitely think Sn2, okay? So 1, 2, 3. Okay. And so then, where are we on? Okay, we're on that one. So that was Sn2. And then our last one here is, you know, tertiary, weak, protic. So that means that, Sn1. Okay. I think you guys are pretty good at this by now. You guys all got this. Sn1, Sn2 stuff. Okay. Let's talk about 7. So I'm just going to go to 7 real quick. So drawn below are these, you know, different reactions, A through C. Draw the key reactive intermediate. Okay, so that should give you like a hint. Which reaction do I know? Sn1 or Sn2 goes through a key intermediate. Okay, and it follows the rate determining step. Then draw the final product. So these descriptive words are very kind of big red flags to you that this is Sn1. This is all talking about Sn1. Sn1 is the one that has, you know, rate determining step dependent on that leaving group leaving on its own. So you get this, you know, carbocation. Oh, if your head is ringing like so many different things right now, like go you, because ring expansion. I know you hate me. I know. But it's a ring expansion. Okay, so we get, so we're going to take away, here we can number this. 7. Okay, so now my ring, I'm taking away from 3. So, can't really see, that's positive. So I'm going to call that 1. Okay, so essentially I'm going to 2, 3, 4, 5, 6, 7. Okay, so now on 2, I should have a methyl group. On 3, I took electrons away. Okay, 4, 5, 6, and 7 are all good. Okay, so that would be my intermediate. And you can attack at that position, okay, now with the, you know, methoxy group to get OCH3. Okay, and we don't have to, you don't have to draw the major stereoisomers, but you know what I mean. It's just knowing that that key intermediate could rearrange and then seeing that this is our product that we have. Okay, so here what we're going to see is that this is going to leave on its own. We're going to get a carbocation. I'll draw it over here. We're going to get a carbocation on the secondary position. I can move my hydride over to get a tertiary position. And then I can do one more hydride shift to get tertiary benzylic. So that is my main intermediate. Okay, and then after, you know, you can attack, and then you get this, and you get the stereoisomer, so you get 4 major stereoisomers there. Oh, I put that in the total wrong box. Ah, that's so sad. Okay, whatever. So this is the answer to B. Okay, kind of makes sense. And you can rationalize C is going to do a ring expansion as well, so I'll do that one for you guys. Okay, so I think we're on beta elimination now. I know we're running out of time, but that's okay. We covered a lot. And I just want to read this. I think it's very important for you, like just some words for you. So since nucleophilicity typically, keyword, parallels basicity, there are competing reactions that occur under Sn1 and Sn2 conditions, okay? So that same nucleophile that was able to attack a carbocation in Sn1 is also capable of deprotonating an adjacent proton, forming that pi bond, which is the elimination product. For every Sn1 reaction, we would always expect that E1 product. And under Sn2 conditions, if we have this non-nucleophilic base, such as terbutoxide, we will outcompete the Sn2 product to get that E2 product, okay? So Sn1 and E1 are always in tandem, but Sn2 and E2 are always in competition, okay? So let's see these competing reactions in action below. Mic drop. Okay. All right. So let's see these. So real quick, let's just do a few of these elimination ones. Okay. So E1 or E2 essentially. Actually, this now wants us to do everything. So for the following reactions, determine if the mechanisms Sn1, Sn2, E1, and or E2, and then draw all the products. Okay, so that's easy. Okay, so here, I see secondary. Okay, and I also see. Oh, Kate, is this what you were talking about earlier?
Yeah.
Okay. Yep. I knew it was going to come up at some point. Oh, I don't know, because you're right. We saw that example earlier. That was like, this might be a cutoff. Is it the ethyl?
I actually checked my notes from today, because today was like Sn2 versus E2, and I did see something that said, for the like strong base of E2, the pKa of the conjugate acid has to be greater than 11. So could that be why?
Yeah, that would definitely be it. So I think because again, this is all qualitative. We don't have any numbers here. Like, it's tough to know if this is E1 or E2, but I think if you're, I always thought a 2-carbon thing would be, okay, 2 carbons on an oxygen is a good nucleophile still. So that's why I would think Sn2, but I think it's that ETOH that makes it a little bit weaker. So, okay, let's do this. I'm literally writing myself a note right now. I'm gonna text Dr. Peterson right after. Dr. Peterson. Question 8A, and I wanna get clarification on that one. But my guess is because ETOH is here, it's going to solvate this nucleophile a little bit more than it would be if it was aprotic conditions. So this nucleophile is a little bit weaker. So since it's a weaker nucleophile, it's just going to do the elimination product and not going to do the substitution product. Okay. I know I don't really have a good answer right now. I will get back to you guys, I promise. Okay. So if it's E2, you can imagine there's a proton here. That base OET is going to get rid of that, put it in, and kick it off. Zaitsev. Okay, this would be E2. Here, okay, so this is going to be a secondary, okay, and so we see this bulky base, so we're thinking definitely the elimination product, but is it E2 or E1? Well, it's E2, okay, because, you know, we're dependent on that base coming, and am I getting the Zaitsev or am I getting the Hoffman product? Hoffman, so the reason it's Hoffman is this bulky base, which looks like this, can only remove from that side, okay, and it's E2, okay? LDA is another bulky base, and I'm only gonna get the Hoffman product as well, okay, so LDA looks like this. Maybe with like sodium, I don't know, something like that. Or aluminum, I don't really know what it is. But essentially, it's gonna remove the proton from here, okay? So you get that, so this is also the Hoffman. So Hoff, and Zaitsev so far. Okay, so this is primary. This looks like a good nucleophile, so strong. And then this just looks like a polar protic solvent. Okay, so I said before that the only time we saw this was oxygen. Okay, why am I seeing it again with sulfur? Oxygen and sulfur are on the same group of the periodic table, which means they have the same reactivity. So yeah, when alkoxide anions are dissolved in their protons, like protonated solution, same thing for sulfide anions. Sulfide anions are also dissolved in their protonated solution. Okay, so don't be confused if you see oxygen or sulfur dissolved in their polar protic solvents. But all these things together still tell me Sn2 conditions. Okay, and that's my answer there. Oops.
How was that one different from A being
From A. Okay. A is more, okay, so first of all, sulfur is, no, let me do this. Okay, ethyl here is 2 carbons long. Okay, so it's definitely like heavier, okay? And also, this is a secondary, so this is my gray area. Okay, so this is a really big gray area when we have secondaries. Here, primary, no thinking every time you have primary, okay? Primary is going to be Sn2, it's very steric, unhindered, and that nucleophile is really strong, okay? Remember that sulfur, it's not oxygen. Oxygen has more electronegative than sulfur. So since sulfur is less electronegative, it's more likely to donate those electrons than hold on to them themselves. So that's why, twofold. Ethyl is longer than, just the methyl, and oxygen is more electronegative than the sulfur. So that's actually real time playing with this, Sn2 versus E2. So A is versus D, essentially. You can kind of think about it like that. Okay, so by decreasing the substitution and by increasing that nucleophilicity, we were able to go to the Sn2 product, not the E2 product. If that makes more sense. Yeah.
Okay, thank you.
Yeah, I know it's like really abstract and crazy and yeah, messy. Okay, so I think we have, it's 4. Okay, so this is it all together. So I really encourage you to practice, page 106 on your own. 106, like 9A through G, like this is how you're gonna have it on the test. So you don't know, just do the Sn1 or just do the Sn2. You have to really think about all these conditions together and see which pathway we're gonna go through, okay? So I encourage you guys to try on this page on your own. Maybe we'll talk about it if we have enough time on Monday, and then we're gonna move on to chapter 10 stuff, okay? Hope that helps, and I'll see you guys next week.
Thank you.
Of course, guys.